This is Lab 5, Choose Your Own Adventure. Here is the video that I will be analyzing in this lab. The objective of this lab is to predict the motion of the diver and to investigate whether energy is conserved during the freefall of the diver. This lab begins with analyzing the video of the diver through Tracker. With the data extracted from Tracker, an observed model of the position versus time graph is created. Using some of the information found from Tracker, a computational model is created by using Newton's second law, weight force, and drag force coded in Python. These models are also a graph that displays position versus time. And finally, we will determine whether energy was conserved by plotting the change in kinetic energy, change in gravitational potential energy, and the change in total energy on the same graph. Here are the two graphs found. The first graph is a comparison of the experiment position plot against the model position plot. As you can see, there are very clear differences within the graph, but the general direction is the same. The second graph shows the three energy changes mentioned earlier. The energy principle was not satisfied, as shown in the total change in energy plot being non-zero. More of these two graphs will be discussed later in the video. The data that was extracted from Tracker is shown on the right. Only the time t and y column were used in graphing the observed model. The graph of just the observed model is shown above the data points. The clip on the left illustrates how the data points were collected from the original video. This lab utilizes the fundamental principle of physics, which is Newton's second law. From this law, we are given two equations. The first equation relates the final velocity to initial velocity. Having a net force on the diver will cause the final velocity to differ from the initial velocity. In this case, the final velocity will be greater than the initial velocity. The second equation relates the final position to the initial position. To calculate the net force, two equations are needed, the weight force and drag force equations. All of these equations shown here will be used when constructing the computational models. The energy principle is also used in this lab. The energy principle tells us that the change in energy of the system is equal to the work done by the surroundings. I set the system to be the diver and the Earth. The work done by the surroundings is set equal to the change in translational kinetic energy and gravitational potential energy. The energy principle tells us that the sum of these two should be zero. Here are the equations for gravitational potential energy and translational kinetic energy. Finding the change in these energies just means finding the difference in the final initial values. These concepts will be used in constructing the computational models as well. The values shown on this slide are also used to construct the computational model. All of these values are used in the Python code. Net force is calculated by adding the weight force and drag force on the diver. B is the drag force proportionality constant. I estimate the mass of the diver to be 70 kilograms, and the time frame in the video came to be 1.435 seconds. This part of the code updates the velocity and position of the diver using net force. Net force is calculated using the sum of weight force and drag force. You can see where in the code the equations shown are translated. This next part of the code displays the equations of translational kinetic energy and gravitational potential energy. These are used in constructing the energy change graph that was shown earlier. When the code is run, these three models are constructed. The top left picture shows the position versus time graph. As we can see, the object is not moving at a constant velocity. Rather, it is getting faster and faster as time goes on. It is accelerating. The clip on the right shows the diver's position. You can think of this as the illustration of the original video of the diver falling. The yellow arrow represents the weight force and the small blue arrow on top represents the drag force. If the diver stayed in the air long enough and the blue arrow was allowed to become equal and opposite to the yellow arrow, the diver's terminal velocity would be reached. The bottom left picture is the change in energy graph that was shown earlier. As you can see, the change in total energy was not equal to zero, as the energy principle states. The sum of the translational kinetic energy and the gravitational potential energy came out to be about negative 1.29 joules at the very end. This indicates that there are other energies that are present that were not accounted for. These may include a change in rotational kinetic energy and change in internal energy. If these were included in the model, the total change in energy plot would be closer to zero. The differences in the second graph can be explained by numerous reasons. The unstable, not smooth curve from the experiment position can be explained by the shaky video. The video was not still, so the position of the diver relative to the set coordinate system was not very accurate. It was also difficult to point the exact center of mass of the diver when analyzing the video in Tracker. Furthermore, I was forced to estimate the mass of the diver since there was no information available. I simply used the average mass of a male adult.